about this really interesting topic of radio localization with three or more application areas that we'll learn much more about. But let me just give you a welcome. Thank you for coming to the first seminar of 2024. We run these more or less monthly, so please do come back. Next month, we've already got a speaker lined up on a slightly different topic in habitat mapping ecology. Please look out for the notice about that. But today, we're very pleased to welcome Graeme Woodward from University of Canterbury Wireless Research Centre. Graeme's been connected with the GRI since its beginning, I think. Yeah, so several years, and he's part of the research advisory group, which meets a couple of times a year to discuss GRI research and directions and things. But of course, he does a lot of geospatial work in his own right, and we'll hear about that today. And I know some of the research Graeme's going to talk about, so it's really cool stuff. So Graeme, why don't you come up and introduce yourself a bit more, and then we can get going.
Okay.
And if anyone online cannot hear, please do give me a shout. Graeme, please, the floor is yours.
Great. Thank you, Matt. And thank you everyone for being here online and in person. Yeah, so I'm going to start by assuming I'm not speaking to a room full of engineers. So I will talk a little bit about how wireless signal processing is intrinsic in positioning, modern positioning systems, which we all use day to day when you pull our phone out of our pockets and try to get somewhere, and all sorts of other ways. So I'll start with a little bit of a primer about some of the tools we use for positioning using wireless signals. And then I'll just sample some of the projects that we're doing in the Wireless Research Centre here, which make use of positioning technologies. Right, so yeah, that's just an outline there. So I'll start off with a little bit of a primer, then talk about how we're tracking insects using radio, how we're doing some sport tracking, helping with the sport of triathlon in keeping all the athletes doing the right things, and then some climate change research we're supporting down in Antarctica to measure sea ice thickness. So radio localization, as I said, it's intrinsic in modern positioning systems, and we have essentially three tools to use: propagation time, which is a proxy for measuring distance, angle of arrival, and radio fingerprinting. So I'll talk a little bit more about the first two in particular. I guess I'll square off radio fingerprinting. We're not going to talk about that again. That's just where you build up a map of what the radio environment looks like in a bunch of places, and then as you move about, you compare what radio you're seeing against the pre-measured map. We're not doing any work in that space, so I'll just concentrate on the other two. Okay, so propagation time. The first concept is time of arrival. So, for example, here we have a diagram. It could be a cellular phone system where we have three base stations, the towers there. They are time synchronized. They send out beacons to a very tight time schedule. And the mobile terminal here, MT, determines the time of arrival of each of those signals and hence measures the distance, which is represented by the circles. Now, this obviously requires some very, very tight time synchronization, so you can measure those propagation times and convert them into distances. And then you simply draw circles around each of the anchor nodes, in this case base stations, and where all the circles intersect, X marks the spot. We can extend this to a round trip time of arrival, whereby we send out a signal and we perhaps in the top right here, we have classic radar. We send out a signal and we time how long it takes for that signal to reflect back. And that propagation delay maps into double the range. Pretty standard radar concept. So that's round trip time of arrival. One of the big issues with that is that you have no way of discriminating which target that signal is reflecting off. right? Everything's reflecting. So you can modify that in numerous ways, and I'll talk about a specific instance of that later with the insect tracking. But in principle, you can have a situation where, in this case, a mobile terminal is sending a signal to the base station. The base station does some processing and then sends a modified signal back. So what you've got to do is you measure this time from when you sent the signal out to when you receive it. You subtract the known processing time, so it has to be very tightly calibrated what time you take out, and then you've got the round trip delay there. And there's numerous ways, numerous variations on that. Here we have a photo from a project from a number of years ago where we were doing positioning inside a warehouse for automation and safety, effectively so that fork trucks could operate autonomously, and also knowing where everything is so fork trucks don't come into conflict with pedestrians or workers in the warehouse. So in that case, the restriction is in a warehouse with a metal roof, you don't get GPS. So you can't use standard sort of autonomous vehicle type technologies. So you put some anchor nodes, which this is sort of the back of an anchor node here. These might be stuck around the walls, and these are sending out these signals, and your terminal here you want to know the location of is receiving signals from multiple anchor nodes. It's modifying them and sending them back. And so this signal knows that it can calculate that distance by subtracting the processing time that node takes. All that what I've talked about so far requires a really tight time synchronization between every node in the system. You can relax some of the timing requirements by using time difference of arrival instead of time of arrival. And then you go from solving the intersection of a set of circles to solving intersection of a set of hyperbolas. Same principle though. And then if you want to get really accurate distance, timing information, you can look at the phase of the signal. So for example, here we have a diagram where we have a received signal at one frequency, we have a local copy of that signal, and we can measure the phase difference between what we receive and our local copy, and that gives us a very tight, very fine time resolution and hence distance resolution. However, because the signal is periodic, there's ambiguity. You can see all the crosses in that top line, all the places where that phase relationship would be valid. If you do this at multiple frequencies though, so you do the same thing at a different frequency, F2, and you get a different set of possible positions, and now there's only one point where they both occur at the same point in space. So this is the basic principle behind RTK for satellite positioning for GPS. Okay, so time was one of our fundamental concepts. The other thing we can measure is angle of arrival. A phased array, well used in radio astronomy for many, many years. So I have multiple antennas, and you just measure the phase difference across that antenna array. So you have these wavefronts coming in, and you can measure the difference phase between antenna 1 and antenna 2, and hence determine theta in that diagram there. You do this in multiple places. So you have two antenna arrays, and both of them you can measure the corresponding theta, and then you do a little bit of geometry, a bit of triangulation in this case, and where the two lines intersect, that's where your target is. So that's one way to do angle of arrival. Another way to do angle of arrival, which we all would have seen out at, around the airport, etc., is a physically swept narrow beam. So I have a very narrow focused beam, and you just turn that mechanically, and then you get the range based upon the time, and you get the angle based upon the mechanical angle. Right, so that's a primer of some of the tools we have. Now, how do we go about applying them to some real-world problems? So this problem of tracking insects was brought to us by Dr. Steve Pawson from the School of Forestry here. Wanted to understand the behaviour of insects better and couldn't use traditional biological tools. For example, one of the target insects was cannibalistic. And one of the tools they typically use in biology is that they mark a whole bunch of insects, paint or whatever. They put traps through the environment and they release all the insects at once, and then they monitor those traps over a period of time. However, if the insects have a tendency to eat and maim each other, then you're not going to get very good statistics in this way. So that's just one example of why you might want to monitor an individual insect rather than use some of these more traditional tools that biologists use. So yeah, why do we want to track insects? There's a whole bunch of reasons. Invertebrates are declining and they're an important part of our ecosystem. Just New Zealand has more than 4,000 threatened invertebrate species. And we actually have surprisingly little knowledge about them for conservation or pest management. Well, I guess if they're threatened, we're more in that case concerned about conservation, but nevertheless. So some of the reasons we might want to understand the behaviour of pollinators better. As I said, very important part of the whole operation of the ecosystem. Finding and destroying invasive species, so homing in on nests, for example. Finding something that's entered the country that we don't want to be here. Obviously, we're not tracking that insect because that's the whole point of finding it, but actually we can train other insects to hone in on the pest insect, and then we can track the insect that we've trained to hone in. Understanding long distance dispersal for pest management eradication. I alluded to that with the forestry example where we want to know the dispersal characteristic of particular species of insects, and just understanding the behaviour better, science, understanding how insects behave to understand natural world around us better. Real-time tracking of most invertebrates, insects, is not possible using existing radio telemetry because the tags are typically battery operated and they're too big and they're too heavy, or they require very expensive infrastructure because the signal's so weak, so they need sort of, huge trailer-mounted radar systems or what have you. So here are some of the existing tracking technologies. So even though they're quite small in the context of tracking, say, birds and the like, 220 milligrams, for example, is one of the smallest radio tracking devices around. They're still very large in the context of an insect. They also typically involve things like manual operation. So here's someone with a radio tracker and they have to physically walk around waving this thing, listening for beeps in their headphones to find the signal direction of, strongest direction. Or these huge, I can't remember how much power, but it's in the kilowatts range from this trailer mounted radar system here. So that's quite difficult to access to do a lot of work with. So I should take a step back. So it's first, the top photo is an active transmitter. That was the one down around 220 milligrams. That has a battery. So that continually is putting out a signal which you can hone in on and track. As I said, they're a bit heavy for insects. And anyway, they also cost around $200 US each, and they only have a limited lifetime and 3 or 4 weeks and they're gone. So every time you want to you track, you're throwing away $200 worth of equipment. And then these lower two ones, the reason why we need so much power or we need to walk around and get quite close to the target is because this is using battery-free technology where the signal return from what we've put on the insect is very weak. So we either need to blast it with a lot of energy or we need to be quite close to the target. And they're the last one is how our project is attempting to address. Okay, so a passive tag. Passive meaning not active, meaning it doesn't have a battery. We make use of harmonic radar. Now, the reason for harmonic radar, and I alluded to this earlier when I introduced the round trip time of arrival, radar, classic radar, everything reflects in the environment. So we need to find some way to make our target reflect differently to what everything else is reflecting so that we can identify it in a cluttered environment. So In harmonic radar, we introduce a nonlinear radar response, which means that here's our tag, which we'll attach to the insect. We illuminate that with our radio frequency transmitter, RF transmitter. We pump energy in at frequency F sub 0 into the environment. Everything reflects that frequency back. This tag has a frequency doubling behavior. So it emits something at a multiple of F0. Classically, we use double the frequency, 2F0. So it emits at what's called the second harmonic. And this radio receiver here, this is what we do in the spectrum. So that's frequency there. It filters out our fundamental, our original frequency, and is tuned to receive this harmonic signal. And hence it eliminates all the clutter, all the reflection of everything else in the environment, and can simply measure effectively this path from the transmitter from our tag down to the receiver. Now, in this case, there's no propagation, no processing delay on the tag. It's instantaneous, so we don't have to take off. I mentioned that round trip time of arrival. We might have a processing time we subtract off in the context of positioning using mobile phones. That would be true, but here that's instantaneous, so we don't have to take any time off for that for processing. But we're just we're transmitting at a fundamental frequency, and we are receiving at the second harmonic. Right, so what does a tag look like? A tag is actually really, really simple, which is useful because that means that we can make it cheaply, because these are going to be lost on insects, and make them really, really small. And this is where perhaps a little bit of electronics might be handy. But we're going to use something that looks a little bit like a rectifier, half-wave rectifier. Now, what a rectifier does is it just removes the negative components of a signal. And it does that using a diode. A diode is an electronic component that only allows electricity to conduct in one direction. So if you put a sine wave like this into a diode, in the positive, it'll conduct. In the negative, the diode doesn't conduct. So you put in a sine wave, and what you get out is just the positive bits. Now, if you look at the frequency components of that signal, that's a sine wave, it's just one frequency. So if you plot it in frequency, you've just got the one frequency. If you do an analysis of the frequencies contained here, you have a whole sequence of frequencies. You have the fundamental still, you have the second harmonic, and actually you have a whole bunch of other small components at other different frequencies. So what we've done is we've got a system here where we have a piece of wire, an antenna, which absorbs our fundamental frequency. The diode converts our sine wave into this half-wave rectified signal with just positive bits, generates these harmonics, which we've designed the antenna so that it can also propagate out at that second harmonic. So we've generated these harmonics. The world around us is generally linear in nature. You can't create new frequencies without having a nonlinear component. So back to the classic radar, everything just reflects back the fundamental. You typically don't have anything that's going to change frequency. It's only because of this nonlinear component, this diode here in our tag, that you get this nonlinear response. So the only thing that will be reflecting back typically at double that frequency is this tag with the diode in it. The problem is that the response is extremely weak. We get a bit of physics, but at the fundamental, the frequency, the power of the signal will drop off as the negative force power of our distance. So double the distance, and if I've done my maths right, our power goes down by a factor of 16, right? At the second harmonic, it's d to the minus 6. So double our distance and our power goes down again. If I've done my maths right on top of my head, goes down by a factor of 128. I think I've got that right. No, 64. Anyway, so although we're generating second harmonic, it is extremely weak. It's even weaker than normal, normal radar. That's the challenge. So we've got to make these things. So the tag design is the antenna, which is a fancy way of saying a piece of wire cut to the right length. The diode is a nonlinear component, and as it turns out, we need an inductive loop there, which has to be a certain size to make this whole thing resonate at the right frequency, so that it absorbs the energies that we want. Sorry, it absorbs the frequency that we want to absorb and repropagates that second harmonic in as strong as we can. And up the top left there is one of the pioneers of the area, Bruce Colbitz from Canada. Bruce was out here a couple of years ago to help us with this project. And he was building these tags simply by bending a piece of wire and soldering a very small diode across the gap. But then it wouldn't quite be tuned to the right frequencies. So you'd go to the lab, you'd measure it, you get out a pair of cutters and cut a little bit of wire off and measure it again. And it'd be a little bit like, you know, trying to straighten up a wonky chair. Oops, I cut a bit too much off, and you're back to square one. So yeah, work, some really interesting science done there, but not very repeatable if you wanted to make these tags in, you know, the hundreds or thousands. So our aim is to make something that's much more repeatable. Now, there's a group in Taiwan that were working on using like printed circuit board type technology, making what are called patch antennas. So more than just a straight bit of wire, but these more complex structures where you print it down on a circuit board using sort of photographic type techniques. And there's a picture on the back of a bee, and that kind of worked. But the catch is bees are designed to carry weight. That's kind of their purpose in life, to go around and collect and carry things, right? So they're a bit of an exception in the insect world. We couldn't expect that a lot of other insects would be able to carry such a weight. So these so-called patch antennas are a bit too heavy for the type of environments we want to work with. So we tried to come up with a hybrid approach. This is one of our early approaches, whereby we had a little printed circuit board there, which just had this inductive loop and had the pads where we could place our diodes in a repeatable way using standard sort of manufacturing type techniques, but the antenna would just be pieces of wire off the edge of that board. And we had some really good results with that. We had a postdoc working on it. We published some papers on it. I can't remember what weight we got down to, but it was getting down close to our target weight, but still not quite where we wanted it. But it was a step forward towards the goals of having a repeatable tag performance, reasonably lightweight. So the challenges are to make the tag even lighter, shrinking it even smaller, making it repeatable at volume, maximizing the tag response, and then dealing with the limited range. Even if we achieve all the top one, or tag response, that attenuation distance is still going to be quite a limiting factor, so we have to deal with a limited range. And that's an ongoing project we're working on, funded by MB, and that's what focused for the last couple of years and for the rest of this year. This project runs through to the end of this year. So when we're talking about antennas, the fundamental dimensions of antennas are proportional to the wavelength of the propagation, and the wavelength is inversely proportional to the frequency. So if you increase the frequency of operation of something, then all the feature sizes get smaller. So the previous tags I showed you all operated around 3 gig to 6 gig. We've got to operate in bands that we're allowed to operate in, and their frequency pairs are allowed to operate in. The next option where we had a frequency pair that we could operate in were 9 and 18 gigs, so about 3 times the frequency, and that means everything shrunk down about 3 times the size, which is kind of nice. The kicker though is that propagation actually gets worse as you go higher in frequency, gets attenuated by anything that it doesn't propagate through things, including foliage of trees and the like. So the propagation becomes more challenging, but at least we're addressing the size. So we were now targeting a 1 milligram tag weight, and we were going down to really, really fine glass substrate, 100 micron thick, and using the same sort of technology that you use to make a printed circuit board. And we're doing this with the NanoFab lab over here in electrical computer engineering. And this is a highly repeatable process, you know, same way silicon chips are made, so very repeatable. And we didn't have the skills to do the design of this antenna system ourselves, so we employed Kim Eccleston, who's out at Lincoln Agritech and has this expertise. Kim used to work here at the university. Now, what this diagram here is it's just shows a propagation pattern out of an antenna. So you can see you essentially have a diode there, a long piece of wire, and this little bit in the middle is where the, an antenna here, long piece of wire, and a little bit in the middle is where the diode would go, and it propagates out that way. That's what these sort of structures show. But this is the output of a piece of modeling software which predicts the performance of the tag, predicts the ability to absorb energy at a particular frequency, repropagate at a different frequency, etc. And all that behavior is influenced by what's in the immediate vicinity of our tag. And in our case, we're going to attach this tag to an insect. So I have to model the insect. So this yellow thing here is our model of the insect. It doesn't really look like an insect, but yeah, you've got the modeling software, you can't put an insect in it. You've got to put something in there that represents the insect. But this shows one of the challenges is what we're modeling, what we're designing can only use an approximation of the real world. So we design it using these tools, computer-aided design, etc. But we then have to actually go and build them, measure them, refine them, optimize them. There's an iterative design loop there. Okay, and so this is a wafer of tags without the diodes. It's got the bot where we have to still place the diodes on there. And you can see it's what's called a meandered dipole. I mentioned before that an antenna is just like a piece of wire. Technically, I'm talking about a dipole antenna there, which is just a straight piece of wire. These have been modified a bit to make them a little smaller, what's called a meandered dipole, which just means you bend the ends in a little bit, and that makes it all a bit shorter. But you can see there's parametric variations across, we did about 80 different variations on the theme there. And this is because of the difference between the real world versus the model world. We don't really know what an insect looks like in terms of radio propagation. So we made a whole bunch of slight variations on the theme. And here's one of our tags against a prototype, which used more conventional methods. And we got that down to, it's round about 1 milligram, I think, maybe it's just a little over 1 milligram, which is getting very close to what we want. Okay, so that's the tag design, miniaturizing the tag design and trying to optimize the tag design. The other challenge I mentioned is the range. Now, the best we've got so far is about 15 meters range out of one of these tags. So that doesn't really give you the ability to sort of have your measurement on one hill and watch an insect on another hill. You've got to be much closer. And in fact, our measurement platform has to be able to follow the insect. So we tag the insect, and then it all gets a bit crazy here, but this is research and it's fun, is how about we make the whole radar system mobile by putting it on a swarm of drones. So we have our transmitter, the mothership, if you like, here, which is a drone with a high-powered transmitter, pumping energy down at this frequency, this fundamental frequency f sub naught. And then we have a bunch of receivers on smaller drones which are listening at this double frequency, because remember the tag here on the insect is doubling the frequency, which is why we can spot this insect and not spot this tree. And all these other receivers are measuring that whole time and hence the distance. And then you do some of the geometry that I kind of showed earlier on with the intersecting hyperbolas. And you can, in theory, determine where that target is from these multiple range measurements. And then as our target, our insect moves about, our whole measurement platform moves with it. Now, another way of addressing the weak tag response, as I mentioned, it's got that diode there, right? And the diode needs a little bit of power to turn on, right? And So its response initially is extremely weak until it turns on. So what we've come up with is a method whereby we have our radio transmitter there, bouncing energy off our tag doubles it, we have our receiver here. That's the basic system, that top section. But in order to get that diode to turn on and hence give a stronger response, we've now added a couple of what we call helper nodes, auxiliary nodes, which are just pumping in more energy at the fundamental. They're not doing any range measurements or anything. They're just pumping energy into the system, which it gets absorbed by the tag, which turns the tag on a little bit more, which means it can give a stronger response to our ranging signal coming out of the blue transmitter. And we get hence get a stronger response at the receiver. So that's an experimental method that we've built a radar for. We haven't actually tested this yet. We're very keen to test it. And I'll just skip over that. This is an early prototype of our radar. We're using a consultant, Greg Stores from Auckland, who actually happens to be down here today. And this was our prototype back in 2022. And then today, in fact, he's down here again. Oh, sorry, that was our prototype. This is the innards of the radar that he's just delivered to us. Yeah, and this is testing today in our car park. So this is a new radar unit on a tripod, and you won't be able to see it, but there's a tag up the fence there, and we're measuring the range along the fence. Now that's just with one radar unit, so we're just getting one distance. We need to have 4 radar units, all measuring distances, and then do the geometry with the intersections. And so we're going to be doing that out on the old Kirkwood ovals over the next, well, starting tomorrow. So that's exciting. It's all starting to come together. Our crazy idea is starting to see fruition. Okay, I'll move on to another topic now, and that's draft busting in triathlon. So sport of triathlon, swim, bike, run. In the bike leg, you're not allowed to draft. You're not allowed to slipstream behind another cyclist. It's supposed to be an individual effort. If you're a faster cyclist overtaking another cyclist, there's an imaginary box around the front cyclist, and as soon as you move into that box, you've then got a certain time, 30 seconds, 20 seconds, I can't remember exactly, to get your front wheel in front of the other and then move forward. And the way that's currently policed is that there's referees on the back of motorbikes driving up and down the course, eyeballing, they're too close, how long have they been too close? And, putting up the red card and applying a penalty. But it's all sort of eyeballing. And the athletes also have to eyeball it. They have to judge, am I 12 meters behind, which is illegal, or am I 15 meters behind, which is fine? And so it's all been a little bit, there's a lot of room for error to date. So this idea was conceived by 2 former pro triathletes, Dylan McNeice and James Elvery. And anyone who's been following triathlon might have heard some of those names, particularly Dylan was very highly ranked around the world. So they wanted to address this with some technology whereby you have this wireless technology to measure the distance between bikes. And so this is the unit here, and it has a series of lights there, which the following cyclists can see. So the lights go through a sequence. You're approaching the no drafting zone, you're in the no drafting zone, it starts flashing if you've been in the no drafting zone beyond the time you're allowed to. And the referees still patrolling the course can see this too. And ultimately down the track, all that information will be communicated to a central location. And so the referees would be able to see all this happening remotely. The sport's not quite ready for complete automatic policing of this, where penalties are applied automatically by the system. For one, there's so many exceptions, the system wouldn't be accurate enough in order to reliably impose penalties, but it's certainly a very useful tool, both for the athletes to know that they're following the rules and for the referees to stop having to just make sort of a judgment call on how close they are. So the startup called Race Ranger in partnership with ILR, which is a company just down here in Addington, which does a lot of prototyping and low volume electronics manufacture. four designed for the physical encasings and university wireless research centre. Right, and it uses an interesting combination of wireless technologies. Roughly speaking, every node has a GPS in it, so it knows roughly where it is in the world, but GPS is not accurate enough. We want to measure down to centimetres, certainly sub 10 centimetres, and GPS can't reliably get there. Bluetooth and what's called ultra wideband ranging, which does get us down to that centimetre accuracy. So the basic process is every node measures where it is roughly using GPS. It then sends out Bluetooth beacons, just the same Bluetooth you use for peripherals on your computer. It's just saying, I am X and I'm at roughly this position. And everything else within range, roughly 30, 40 meters, receives these beacons and works out where other athletes are roughly in relation to themselves, and then has a priority list of other athletes which they need to make an accurate ranging to. So the nearest following athletes, for example. And then it uses ultra wideband to get a very accurate measure between the bikes. So this bike has a node on the back seat. This bike, every bike has a node on the forks. So this sends out, this is the round trip time of arrival measurement. This sends out what's called an ultra wideband sounding signal to this one. This one receives it, sends back a modified version so it can uniquely identify this bike. And then the signal processing here determines that exact distance and then controls the lights appropriately. So these are some prototypes and some testing. And here, hopefully the videos work, is some testing we did out on Canterbury Plains with a couple of athletes. So these are more or less simultaneous. So you can see that the on the front athlete, the node here, oh, actually, no, it's there, but there's a camera so that we could determine what was happening with the lights. And James went out there and put these stakes into the ground at exact 10 centimetre intervals early in the morning before the test. And then we had a couple of people hanging out the windows of a couple of cars. So we could measure how well it was actually working in practice. We're trying to refine how we test these things because that's not a very convenient way of testing. But as an early test, it did the job. Okay, so I don't think you'll be able to see lights coming on and off, but yeah, it was just this one cyclist was just slowly closing in on the front cyclist and just looking at that threshold of when the lights came on, and then comparing it to counting the number of poles to see how it was performing. Okay, and that was successfully used in competition at PTO, which is one of the organisations running professional triathlon competitions around the world, in Ibiza last May. And since then, it's been used a lot over last European summer. And it's, I think they've got something like 40 events signed up for this European summer, also in North America. And it's going to be used at the Paris 2024 for the Paralympics. And it's become, it's actually the athletes are now calling for it because they like a fair competition. And before there was a lot of cheating, a lot of people bending the rules. And they see this as a road to having much fairer competition, particularly as all the statistics can be downloaded after the event, and the event organisers can have a profile and they know which athletes were bending the rules and which won't. So even if they're not going to apply penalties here and now, they know that at the next event, they have to keep an eye on that athlete, because last time that athlete spent, over a 3-hour event, spent half an hour illegally drafting. So we'll keep an eye on him or her. Okay, the final topic that I'm going to cover is Antarctic sea ice thickness measurement. So the motivation for this is climate science and improving the way that we can measure the thickness and hence volume of sea ice, because satellite monitoring systems are just not accurate enough. So what we need to do is we want to actually know the thickness of the ice. So this is a cross section here. We've got the water, we've got the air, and in between that we have snow sitting on top of ice. And what we're interested in is the actual ice. We don't want to measure the thickness of the snow, and that's one of the main challenges with this. So we use a combination of technologies. Well, when I say we're supporting Gateway Antarctica here. So we're only doing a very small part of this. We're helping them out with some of the wireless technology. But this is really the Wolfgang Rack and team over in Gateway Antarctica. This is their work. But from a airborne platform, you can use laser, for example, to measure the top of the snow. You can use radar to measure, well, actually both the top and the bottom of the snow. And then you use something called an EM bird to measure this interface between the solid ice and the liquid water. And what we want to do is combine all this together so that in one flight, we can collect data on both that, and hence take the difference to get the real thickness of the sea ice. So this is the EM bird I mentioned. So it's a big thing that's slung off the bottom of a helicopter or an aeroplane. And it puts down pulses of energy, and that causes eddy currents in the liquid, so the seawater, not in the ice, and that causes a back propagation, and then you can do the same sort of thing I mentioned before, sort of a round trip delay, and you can measure this interface here using this instrument. So that's not something we've had worked with directly. That's the EM bird. What we've helped with is this snow radar, which is measuring the top and bottom of the snow. The other important part that we need to know so that we can extract that distance there. So it's an antenna system here with which uses a frequency modulator continuous wave radar, step frequency over a wide bandwidth. And the part that we were working on is interfacing that to the electronics so that it could collect data very quickly from a moving platform. It's one thing being able to measure a static, but when you fly this across over ice, it's got to do this processing very quickly. And furthermore, helping to shrink the whole process down, the whole structure down so that it can be flown under a drone or integrated with this EM bird. So here we are with the 8-rotor drone that was built up in our centre. So the first version of the snow radar was shrunk down to a smaller form factor here. This is together with people out at Lincoln Agritech. Interfacing this high-speed vector network analyzer, which allowed us to collect data while on the move. And then this was taken down and flown in Antarctica, and I'll have a video of that later. And this is some of the data that was collected, and you can see there's a radio echogram on the left there, where you can see the difference between the two bright patches is basically the thickness of the snow, and taking cross sections there, you can see there's distinct peaks indicating the air snow interface and the snow ice interface. Reason being that the radio waves propagate back more strongly from those interfaces than they do from other parts, or the more homogeneous parts of the snow. So the next phase after flying it successfully off a drone was to integrate it into the EM bird. So the EM bird I showed you before, which is measuring the ice-water interface, and then housing this snow radar in the back, and then developing the data collection methods so that the simultaneously you could collect the data off the EM bird plus the snow radar to get that distance. Okay, and I'll just finish off with a video of the drone flying with the snow radar over Antarctica. So it'll come in closer so you can get a bit of a closer look at the antenna too. But while that's playing, I'm happy to take any questions.
Thank you, Graeme. Really cool tech being used in interesting ways, and really kind of like, especially.
Yeah, it's just a drone. Yeah.
So, yeah, question. And if there's anything online, then just please do. See, there is a question online already on the loop. I'll come to you with the loop. In the room. Yeah.
I don't know how they do it at the moment. In cricket, there's loads of debate over this modelling system that estimates where the ball has been and where it is to go. And I think it's based on the trajectory they've got up to a point. And I just wonder whether that system you've got cycle that insect could potentially be another way of doing behind the actions.
It can be used in together. Yes, what you're describing is the next step of the problem, which is the tracking. What I've talked about is positioning, right? So positioning, because you typically take a block of data, process it, take another block of data, process. What you end up with is a breadcrumb. You end up with a series of dots in space, right? How do you join those dots? How do you smooth out the inaccuracies and noise in every dot? So that's where you come to some filtering and some tracking. So you can also determine, for example, velocity. Not only, I mean, obviously you could determine velocity by, you know, the distance between two dots and the time it takes for them to move. But you can also use Doppler shift when you bounce signal off an object, it would bounce back at the same frequency. But if you're moving, you know, the classic Doppler with the ambulance going past, right? The pitch changes, right? So the waveforms get bunched up if it's moving towards you, or they get spread out if it's moving away from you. So you can also use radar to measure velocity. So absolutely, you can combine your points in space along with velocity, along with a motion model of what you're tracking. So a motion model for a cricket ball would be different to a motion model of an insect, but yes, you could combine those models and hence have a much more accurate track of whatever it is you're trying to follow. Yeah.
Just people online, I might repeat the question. So we get that. Yes.
Yeah.
Are you in some insect tracking needs that we have here on campus in terms of urban insects, and would the urban environment be an issue for this?
Yes and yes. Well, okay. So, are you part of the biosecurity cluster? Okay,
Like,
probably should be. So, I'll put you in touch with Steve Pawson, who's running that research cluster, and he's an entomologist. He's really interested in related problems. So yeah, we'd love to find other ways that we can apply this. We are testing this technology now. The technology side of things, but the next step, once there's quite a big step to go, but we want to start using it in the field on real insects. Probably going to start with snails first, to be fair. It's a little bit easier, but yeah, moving on to real insects. Now the second part of your question, using it in an urban environment, yes, that does add extra challenges because we've got a drone swarm here, right? And at the moment we're using it in places, open fields like Island Fields. Flying amongst trees and the like is a little bit beyond us right at the moment. But that doesn't mean there might be parts of our technology we could use for a more cluttered environment. Yeah.
Regarding the insects, I'm just wondering how the system, the whole drone system, how many insects do you think you will be able to follow, to track?
One, unfortunately. Yeah. Because of the extreme limitations in terms of how much we have to shrink these tags down and make them super light, they are only capable of frequency doubling. And so, yeah, we can't distinguish between two different targets, not yet. Now, there are some things we can do, for example, combining the tracking idea. If you know where they start, you can track them as they move around. And as long as they don't sort of go to the same spot and stop, then chances are you can keep on tracking them, right? Even if they cross paths, hopefully you can infer from their motion models and their velocities that they've just crossed, but there might be some ambiguity there. So we might be able to track multiple targets using some clever tracking technology. Also, our previous postdoc, who's now taken up a permanent position in University of Twente in Netherlands, she's looking at trying to add some frequency selectivity tags. It won't be very selective, but it might be that you can get maybe 4 or so tags across the bandwidth, whereby some of them, they have a bit of a different frequency response. And that would, again, combined with some tracking technologies, you might be able to track a small number of targets. But it's to come up with the contrast. It's not like an RFID, like your access card or whatever, whereby every insect, you're going to have 1,000 insects and they'll all be given individual identities. You can track all 1,000. The technology is not capable of that. Yeah.
Thanks. Luke has said it's a great talk, interesting topics, 2 questions. So we'll start with the first one. Is there any work done to integrate the draft busting tech into the cyclist head units? Currently, there are products like Garmin Barrier that use radar detection and display an approximate angle and distance of vehicles behind. Could the following distance be displayed in real time using your technology?
Using the technology, yes, it could be. Integration with the Garmin Vario, whatever, has been discussed. However, it's quite a different application, and yeah, it's not likely to have enough interest to commercialize it in that sense. But yeah, Garmin use different technology. They don't use ultra wideband. Yeah, so some interesting thoughts there, but for the moment we haven't really we're not really pursuing that.
Okay, second question, does the insect radar cause a significant amount of heat when interacting with the antenna, and does this cause problems cooking the insect?
No, because well, unless the insect flies really close to our transmitter, no, but that's one of our fundamental problems. We're actually dealing with really, really weak signals here. So our receiver has to be really accurate and be able to pick really, really small signals out of background noise. So yeah, by the time the energy impinges upon the insect, it's very small. It's not going to, if that's the question, it's not going to sort of heat up the insect or cause the insect any issues. Yeah.
Insects are okay.
Yeah. Well, actually, so a little bit related to that, of course, is we're trying to follow these insects, but not and understand their behavior. We don't want to modify their behavior, and so we do have to consider how much weight can an insect carry, and its physical form factor. If it's too bulky, is it going to affect their behavior? And there's not exact science on this. There's people out there that use rules of thumb about 10% of body weight for most insects. A bee I gave as an exception to that. And we did some experiments in the wind tunnel over here at McEng where we glued ball bearings on the back of insects and observed their flight and sort of how heavy could we glue these ball bearings before they started modifying their flight. So there's a bit of work there, but yeah. So we definitely don't want to modify the insect behavior either by cooking them or loading them up with weights. Going to invalidate what we're measuring.
Yeah, it was just related to the behavior because it's something that probably is going to be affected. And for how long, is any studies looking at how long the behavior gets affected and if they come back to normal behavior and then the measurements will be more accurate? Or?
Well, our aim is to make the tag small and light enough that it doesn't affect their behavior. But I guess that's still got to be verified as more experiments. Yeah. It's trial and error because, as I said, we kept on loading these insects up with ball bearings until their flight trajectories went more down than straight. But even more directly, we influenced their behavior because we were using a dental glue which we set with ultraviolet light. And a lot of the insects seemed quite disorientated after we'd glued ball bearings on them. And we've figured that we were actually blinding the insects, which rather affected their behavior. So yeah, we have to come up with a better way of attaching these things to insects. And ideally we get to a situation where they just go about doing their thing, oblivious to the fact they're carrying a radar tag on them.
their protocol use about the dial, use the photo dial, like use the sun to make it work.
Yes, not. We did look at something like that. It wasn't sun. I can't remember. There was something. It was quite a few years ago when we looked at that. Yeah, we were trying to scavenge some extra energy to try to.
Save the track.
Yeah, to try to bias that diode on a little bit so that it's in an area that responded better. Yeah, I can't remember if we discussed that. We are not pursuing it currently, but that's a a really good idea and something we might come back to. It's all about improving that tag response. If we can increase the range, then makes our system much simpler. I mean, partly relating to that previous point, this drone swarm has the potential to affect the insect behavior, right? If we're too close, the rotor wash and the noise, etc., we're going to disturb what we're trying to measure. So we want to be far enough away that we're not affecting the insect behavior. And that involves, the more range we can have, the simpler our tracking becomes, the less chance we have of losing the insect. Because again, if we're kind of close in around the insect, even if we're not affecting the insect's behavior, it might suddenly dart that way and get out of this imaginary box, with our measurement system. So yeah, anything we can do to improve that tag response is an advantage.
Yes, got a last couple of minutes. So 2 more quick questions. That's great.
Do a drone will have to be tracked where they are?
Yes. GPS at the moment. Yeah. But yes, that's we have to have very good timing synchronization between the drones, and we have to have very good location information about the drones. And both of them we use GPS, the GPS timing and GPS location, but raw GPS may not be enough. So we may have to use some augmentation system, but we haven't got to that point yet because at the moment we're testing these up static poles. Yeah, and we're developing the drone swarming technology completely separate. But when you come to bring them together, then that's definitely an issue we have to address. One thing that makes it slightly easier is we only need to know relative position and relative time. We don't need absolute position and time. Like we don't care which, for argument's sake, we don't care which side of Island Fields we're on, but we just need to be able to track, the finer movements of the insect. So yeah, GPS, the relative accuracy between 2 close nodes is way better than the absolute accuracy of each individual node.
Actually, comment. I was wondering if you wanted to mention, for example, the case of downwards and use of the horizontal items. Why it's really one case that's important, even if you track one insect and get to know the behavior of that.
Okay, so I said at the beginning, one of our motivations was to be able to track pest insects. In fact, that was one of the reasons the entomologists in School of Forestry came to us. And that's got critical economic impact to New Zealand because forestry is one of our biggest export industries. And if timber should turn up in a foreign port with live insects on board, that becomes a big issue and jeopardizes future exports. So this dispersal characteristic of insects is very important. Insects get into fallen timber, rotten timber. So you cut down a block of timber, you leave bits scrap around, insects get in there, right? And then a month later, you come down and chop down another block of timber 1 kilometre away over a hill, and the logs sit there for hours or days before they're put on trucks and taken away to port. What we really want to know is how long it takes the insects to get from where their infestation is to the timber that we're planning to export. So it's all about risk mitigation, understanding that risk. Currently, they deal with it by fumigating the timber at the port at export, and that's nasty chemicals. We've signed up some international treaty to reduce our dependence on methyl bromide, which is a greenhouse gas. And so, yeah, if we understand insect behavior better, then we have tools to better manage that risk so we don't put our forestry industry in jeopardy by having live insects in exports. It's one of many different reasons to be tracking insects.
All right, we're out of time. It's now a minute past 2, so apologies for overtime. Thank you, Graeme, for a really fantastic talk and full of cutting edge technology and microphone. So it's really awesome. Thank you. Please do have yourself more sandwiches or coffee. In April, I'd like to get the day now. April the 5th is our next seminar. With Christine Bank about asking a question how much habitat is enough. It's an important question. So thank you, Graeme, and thanks everyone for coming.
Thank you very much.
Thank you. It's great talk.
Nice to see you.
We'll contact you soon.
Thank you.
Graeme, you have any problem if we put